Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
I'm really excited to be here at Saturday Morning Physics. When I was looking at moving to Michigan and joining the department, I heard about some of the activities that we have with the community and heard about Saturday Morning Physics, and I thought that just sounds great. And I'm just really excited to be here bringing my work to you guys and sharing my enthusiasm with you and feeling your enthusiasm for my work come back at me. I think it's just really great, and I'm really glad that our community has this. So what I'm going to be talking about today is the cosmology with a cosmic microwave background. And I really kind of like making fancy slides. And so when I do a talk, I like to think about what am I going to say and try to capsulate it in one big slide. And so I did this for this talk. And so if you look up in the upper left-hand corner, you see a little graph that you can barely make out, and it's not really clear what it is. That's inflation. We don't understand it that well, so you shouldn't be able to see it that well, because we don't know what it is. And it ends in the Big Bang, from which lots of stuff happens, but you get this about 300,000 years after the Big Bang, you end up with this radiation that has these very beautiful patterns that look like noise, but that noise actually tells you a lot about the initial conditions of the universe. And so observing that is really one of the key things that I work on. Then later on, that light has to come to you from about 14 billion light years away, so basically the edge of the universe, the farthest we can see away. And as it does, there's little dark clouds hanging in there, which are supposed to be neutrinos and dark energy, and those subtly affect the light as it propagates, leading to signals that you can observe to learn about the more recent universe. And then, of course, if you're going to build an experiment, you have to make sure you understand what you're seeing, so you've got to avoid seeing the galaxy, which is in the front, and then you need some really nice instruments to actually go and do all of this. And the work I really do is working on building telescopes and cameras and things like that to go out and observe this radiation and learn about the first moments and what's in the universe. Now, when I started putting this talk together, I realized that's a huge amount of stuff, and I have to focus a little bit. And so what I'm going to really talk about is this, how we got to the point of studying the CMB. So there's a little bit of history. And then I'm going to push forward towards inflation in the beginning of the universe, because I think that's a really interesting direction to go. And then in the very end, I'm going to come back and talk about the South Pole Telescope and a camera that I'm working with a team of people on to put on the Atacama Cosmology Telescope, which is in Chile, to sort of push the envelope on what we know. So we'll start by talking a little bit about cosmology in the abstract. And if we could just dim that light a little bit so you can see this picture a little better. What this is, actually that spotlight would be great. If you could just take, oh, it doesn't matter. Anyway, if you look up in the upper left, you can get a better feel for this picture. So when I think about cosmology, I think about, how did we start asking these questions? And this is just a photograph I took when I was down in Chile a couple years ago of the night sky as you see it with your naked eye on a mountain when you're at about 17,000 feet. I have to say that you have to have oxygen breather, because there's only about a third of the atmosphere up there, and your eyes actually start turning off and you can't see that unless you're breathing oxygen. But when you look up at something like that and you see the Milky Way, you see the small Magellanic Cloud up to the left, you just think that's really beautiful, and you start asking, how do we fit in with all of this? And that's exactly what cosmology is. Cosmology is the discipline that deals with the origin and structure of the universe. But since cosmology is a really broad definition, it also includes doctrine describing natural order. And so, we could have a great cosmology talk where we talk about how people have thought about this since the beginning of recorded history, and we could go arbitrarily far back. And, frankly, someday I really hope I get to give that talk, because I would love to know exactly how people were thinking about this. I mean, this picture is just really interesting to look at, right? You've got, high technology in Egypt, which is people that are painted like stars, and so clearly that must be what's in the background. And there's all sorts of interesting stuff you could probably learn from this. But this is Saturday Morning Physics, And so we really want to talk about more modern topics and not about the ancient sort of ideas that people had. But one of the reasons I wanted to show you that old idea is that for a long time, I mean, up until maybe the 60s or 70s, people regarded cosmology in physics as a little bit of a fringe science, because there was this history of people just sort of guessing. And in physical cosmology, people have moved from this idea of just making up stories to help us figure out how we fit into the universe to actually analyzing it in terms of physics and the laws that we know. And so, as I've sort of alluded to, physical cosmology is the branch of physics where we actually try to understand how the universe works and apply physical laws. And then if you look down at this bottom paragraph, I just sort of looked on Wikipedia to see if there were great ways to explain this. And something I really like that's going to be kind of a theme of this talk is that physical cosmology, as we now understand it, began with the 20th century development of Albert Einstein's theory of general relativity and better astronomical observations. And it goes on to give a little more details, but the key is that there's this interplay between theory on the one side and experiment on the other side. And you really, to understand how modern cosmology, modern physical cosmology comes about, you really need to think about both things and how they go hand in hand. So a very good starting point is Einstein's theory of general relativity, which can be written as this in the form of this yellow equation. And the key thing when you look at an equation is that no matter how complicated it is, there's two parts of it. There's a left side and a right side. And if you can understand what's going on the left side and the right side, you can learn a little bit about what the equation's trying to tell us. And so in particular, on this one, you really have two things. You have curved space, which is all that complication on the left, and you have stuff in the universe. And if you can sort of look into the background of this graphic, you'll notice that I've sort of represented how this works pictorially. So if you have stuff in the universe, say some star, that's the yellow sphere, and then you have curved space, that means you have space that sort of gets distorted when it gets near to that other object. And if you want to understand how you make a theory out of this and how you think about it, John Wheeler did an excellent job summing it up in a very short number of words. Matter tells space how to curve. So if you put matter in the universe, it's going to sort of bend things. And space tells matter how to move. And so if you look, there's this sort of red line that goes around the back. And the point is that if you took a planet, some light, whatever you want, and shot it around the star, it would bend according to the space-time. And so space, this curved space, is actually what controls, tells matter, what's going on gravitationally. Now, it doesn't take long to think about this to realize that once you have this type of theory, you could easily make a model for the universe in which you fill the universe with stuff and you describe the sort of fabric of the universe as space-time, and you can build up a really nice model. And so then once you have this sort of idea, if you can figure out what stuff is in the universe, you can understand all about how it's evolving and know its history and do all sorts of really beautiful work. And so this discovery by Einstein is really the dawn of modern cosmology. Now, an interesting note is that there's that third term on the left, which has a lambda in it. And if you think about general relativity, where you have matter and space and they're all evolving, it's almost obvious that you can't have a static universe, that things have to be dynamic and moving. But at the time, people really believed, in the early 1900s, they really believed the universe had to be static and eternal and basically about the same as it is now, always in the past. And of course, we now know that's not true. But if you think about it, that's actually a quite reasonable thing. I mean, for all of recorded history, the stars have been in the same place. And you have to think on a vastly longer timescale to really figure that out. So Einstein, made sure that his equation was consistent with his idea of what the universe should be, and made it static. So theory allows us to come up with a model for what the universe should be, and you can put in predictions for what it should be. But then to really make progress, you have to actually go out and measure it. And another thing that was happening sort of around the same time is that people were really getting a lot better at astronomical instrumentation. And so this is a picture of the Hooker telescope. It's a 100-inch telescope, which is quite big. It's a couple meters. And it's actually up in the hills behind Pasadena, right behind where I grew up. And occasionally they would, when I was a kid, they would open it up for field trips or just for open houses. And you can actually go stand at that railing and see something that looks very much like this today. And one of the really fun things from when I was a kid was going to do this, and they actually let me go down near where the mirror is, which is on the back of that telescope, and you can touch it, and it actually looks like wine bottles, because the glass that they could get at the time was from French wine bottles, and that's what they melted down to make the thing. And it's just, it's a real piece of equipment that people thought about building and figured out how to do with technology in the early 1900s. And at the time, it was the largest telescope in the world. And LA, believe it or not, the reason it's smoggy is that you have an inversion layer, and that same reason means that the air is incredibly stable when you go up in the mountains behind there, because nothing can really leak up, in a way of saying it, sort of non-technically. So this was just an absolutely fabulous instrument at the time, and it really allowed lots of astronomy to move farther forward. And in particular, Hubble, who is a very, very famous cosmologist, was interested in understanding these spiral nebula, which people didn't really know what they were at the time. They didn't know how far away they were, and they didn't know what their origin was. And people all assumed that they were in our galaxy, and they were just balls of gas. So with his observations, where he sat in this little rattan chair and carefully steered this telescope all through the night, he was able to start, not only imaging stars, but more importantly, he found a class of stars that he was able to know that they had a calibratable luminosity. So he could know the brightness by observing how quickly they flash. These are called Cepheid variables. And what was amazing about that is that if you think about it, if you have a flashlight and you stick it in your eye, you're going to go blind. If you stick it across the room, you'll see it, but it'll be dim. If you take it miles away, you won't be able to see it at all. And so if you can measure the brightness of something, you can estimate its distance, close, far, farther away. And so doing this, he was able to figure out that the distance to these spiral nebula, or which we now know are galaxies, was vastly larger than the size of our own galaxy. And so this brought about a major revolution in our understanding of what our universe looked like. It was no longer just our galaxy, it was vastly bigger. But then there was something even more important, which is that he could measure the distance to lots of these things. And so he had a sample of, I don't know, something like 50 of these objects, and he could measure their distance, which is the graph up in the left. And so the x-axis is distance. But one thing that you can get out of astronomy that's very easy to measure is velocity, because there's just a very easy way to do that by measuring basically atomic emission lines. And so he could plot the velocity on the y-axis versus the distance, and what he found is that the farther away something is, the faster it was moving away from us. So that's remarkable in a number of ways, and it's something that you wouldn't necessarily have guessed at if you thought that we lived in a static universe. And so the question is, how do you interpret this? Well, right away, he knew that general relativity was going to be the way forward, and so he sent a letter to De Sitter, who was a smart theorist who was working on expanding universes in the context of Einstein's general relativity. And it was very clear to them right away that this was consistent with an expanding universe. So how do you think about an expanding universe? Well, first, we need to think a little bit about what space is, because we're going to have expanding space, not just an expanding universe. What an expanding universe means is that the space is expanding. So what is space? Well, one way to think of space is a coordinate system, so it's x, y, and z. But just for the purpose of this talk, let's just think graph paper. And so if we could just measure, the graph paper of the universe, to speak very crudely, and see how the size of the cells is changing with time, we'd be able to understand the expanding universe. But of course, you can't really do that. There is no, nice ruled lines in our universe. So instead, you have to look at objects. So you can look at things like galaxies, supernova, stars, and I'll just represent them with little stars. So if we have space, we can think about expanding space. And so we can think about, having our space filled with stuff. And in general relativity, you have to be somewhere to look at things. And so we can imagine being here on one of those stars or galaxies or whatever. And right now, this is at time equals 0. Now, of course, just to make it fun, we don't want to have an empty universe. We'd like to have friends. So we'll put an alien over there. I had fun drawing that. I thought it was a really cute drawing. I'm glad you guys like it too. And then before we start things moving with time, let's just recall the definition of velocity, which is that it's change in position with respect to divided by change in time. So as we move forward, we're just going to put little dots where all the stars were before, so we can get an idea of what the velocity is. And so we move forward by one time step, and things move away, and you can sort of see that everything, the key is that the stuff didn't really move. It's sitting at the same coordinate position, just the graph paper blew up. Right? So that's what expanding space means. It means that you actually have changed the space between things, but the things are really at rest in some sense. They're not really moving with respect to the graph paper. They're just sitting on it and being carried along. And if you notice, all the red dots are closer to the U than the stars, because things have moved away. That's what you expected. And so everything's moving outward from you. The other thing to notice is that the farther you go, the bigger the change in distance, and that's just because there's more space to expand between you. And so you can carry this forward. But the key is that if you really pay attention, the farther away something is, the faster it's moving away from you. And this is exactly what Hubble saw, and so this is the way to think about expanding space. Now, I know that when I first learned about this, my mind was completely blown, and I thought, well, clearly that means we have to be in the center of everything, because everything's moving away from us. If it's moving away from us, we must be in the center. And that seems logical, but if you really think about it, there was nothing that special about choosing where we were. We just chose to be on that star and observe the universe from that point of view. You could ask the question, what happens if you look at it from the alien's point of view? And so you just go over there and say you're the alien now, or you're thinking carefully about him and empathizing with his point of view in the universe. And if you run the same analysis, what you find is that he'll say, no, you're totally wrong. I'm the center of the universe. And there's no way that both of them are right. They're just incredibly egotistical. What must be true is that every point looks the same, and so from everyone's point of view, it just looks like the universe is expanding out from them, and that's exactly what is consistent with just expanding space. So we can't be the center, and expanding space, this is how to think about it. So by around 1930, the observations were in. We had a model of the expanding universe. And Einstein went and paid Hubble a visit. Hubble has the pipe. Einstein's posing, looking through the telescope. And Hubble's smoking a pipe, which means this is a posed picture. And I'm stealing that from John Carlstrom. But if you think about it, if you're a scientist working on a telescope, what's the worst thing you could have on the mirror? Like dust, soot, things like that. So he's totally posing and just looking smart by having a pipe and being a 1930 scientist. But by this point, people really knew that there was something to physical cosmology. We now had a model where the universe was expanding, and that had been observed, and GR seemed to do a good job describing it, because you can think about expanding space in the context of GR. But of course, old beliefs are hard to get rid of, especially when it seems so crazy you only have one piece of data. So a lot of people held on to these steady state theories of the universe, where the universe was just sort of sitting there, somehow fooling these observations, and maybe GR was wrong, but they could even try to make models of the steady state universe in that. So clearly, what you need is to think about more implications of the theory and come up with more evidence. And at this point, I'm just going to completely drop any pretext of being running in a historical sequence, because there's all sorts of stuff that I could talk about. And I just want to kind of lead us towards one of the next major discoveries, which is the cosmic microwave background, by saying, what happens if you take an expanding universe and run time backwards? So if you can think about that, if it's expanding now, it must be compressing in the past. And so you could probably come up with a picture that looks something like this. I'm guessing that the universe is huge, so maybe there's a lot more aliens, and frankly, I just took the other one and superimposed it a bunch of times, so I got a lot of stuff piled up. And so you'd expect that things would get really, really compressed as you go back in time. But this is really not that accurate, because it wouldn't have really looked like individual stars. Those didn't form till late, and also the temperature would get really high, so things would break down. So what you really would have early in the universe is a very hot, compressed plasma. So it's so hot that protons and electrons separate, and these little dots are supposed to be protons and electrons, respectively. It's an artist's conception, or actually it's a physicist's conception of what an artist's conception might look like. Let's be totally honest about what my profession is. And so the electrons and protons separate into this hot plasma. And if you think about it, where do you get hot plasmas? Well, basically burning is one really good way to do it. So the entire universe must have glowed sort of like the surface of the sun. So if you think about it, back in time, the universe must have just been glowing, glowing hot. And of course, I'm not the first person to think of it. It's not even my idea. This all came up in the 60s when people started asking this question. And so now I want to talk about this really remarkable thing where we've been talking about the interplay between theory and experiment. And it's sort of amazing that sometimes that interplay between theory and experiment, people thinking about things theoretically, and the experiments to measure them happen fortuitously at the same time. What's even more amazing is that sometimes those happen within 30 miles of each other or 40 miles of each other, and that's exactly what happened with the cosmic microwave background, which is the discovery of the cosmic fireball, or this plasma that filled the universe. And it happened in New Jersey. And so in Princeton, a scientist named Dickey and Peebles, Roll, and Wilkinson sat down and started thinking about this. And Peebles came up with calculations and figured out that the universe, if you looked out to distant reaches, you would see this light coming from the cosmic fireball. And that because of the expansion of the universe, that light would be stretched to longer wavelengths. And so that he expected you'd see microwaves that were about, something like 50 Kelvin. He wasn't far off. So then, with that prediction, Dickey, Roll, and Wilkinson started building their experiment to go look for this. And they were really far along. And they were very, very proud of what they were doing. So they started talking about it a little bit because they just knew they were so much farther along than anyone else could possibly be. Well, across the state, there were a couple scientists, Penzias and Wilson, who were working at Bell Labs just understanding radio for communications purposes. And so this is the antenna they were working at. You can actually go there as long as you sneak onto a Bell Labs campus, you can still see it. It turns out that I did my thesis right next door to that, so I spent a lot of time looking at this thing. But this is the state-of-the-art telescope that they had to work with for microwaves or centimeter wavelengths in the 60s. And so Penzias and Wilson kind of had this prediction for how well their receiver should work. And they understood how the atmosphere was working. And what they found is that as they characterized this thing, they just found some excess noise that they couldn't explain. It was about 3 Kelvin, 3.5 Kelvin. And they did all sorts of tests. They taped seams that could be leaking light from the ground in. They also had this, another candidate for the source of noise, which was pigeons. And so if you just go right down this hill in Bell Labs, what you'll find is that this is in a residential neighborhood. And why is that important? Well, how do you deal with pigeon droppings as a background if you have nesting pigeons in your telescope? Well, we might use humane traps because we live in Ann Arbor, and this is 2011. But back then, there was a much simpler solution, which is that Penzias went home, got his shotgun, and started blasting away at pigeons. And it's really true. And they did this, and then they found out that actually they didn't need to kill the whole family of pigeons, that it wasn't causing the problem. But they were really exhaustive in all the things they thought of to figure out what this radiation was. And at the end, they concluded that they had no idea what it was. Now, it might have ended there, except that all the people from Princeton were out giving talks about, were talking to their friends about this great experiment they were doing. And so a friend, or actually the way I've heard it, someone who saw Peebles give a talk down at Johns Hopkins, called their friends at Bell Labs and said, I think I know what's going on with your experiment. I think you've discovered the radiation left over from the Big Bang. So of course, this led to an instant phone call from Bell Labs over to Princeton. And as I think Wilkinson told me, they were, the whole team of the Princeton scientists were sitting in their office, or in Bob Dickey's office, and Bob Dickey looked at them and said, well, boys, we've been scooped. And so it takes about an hour and 10 minutes to drive from Princeton out to Bell Labs with the old roads. But I'm told that they managed to do it in about 45 minutes because they were pretty excited. And it must have been absolutely terrible to find out that the thing you've been questing after has been discovered by someone else. But at the same time, it must have just been so exciting to realize that you're looking at the radiation left over from the Big Bang and that this expanding universe picture just has to be true. So they did a really nice thing, which is that they decided that they would publish jointly. And so I just want to show you what their papers look like. So this is both papers in their entirety. You can't see them. That doesn't really matter. There's a couple points I want to make. I mean, first off, it's just really nice that they did that, right? So the Princeton people focused on the theory. The Bell Labs people focused on the measurement. And if you've ever wondered what a Nobel Prize paper looks like, you might think that it's really complicated and written in this really learned English that's supposed to be complicated and only approachable by experts. Well, this is the entire paper. I've circled it. It's about a page. And in fact, the only part that really, the part that got them the Nobel Prize is circled right here. You can't read it, but it just says 3.5 Kelvin background with it, detected at high significance. And I just wanted you to know what that looks like. It's also a really good goal to think about when you're, let's say me and trying to write stuff, that you should just try to boil it down and not belabor a point. But also it really helps if you have excellent content and not so many of us get as lucky, as fortunate as that. The other thing is that if you look up there, there's only one graph in this whole thing, and I'm not going to, spend too much time on it. But if you look at this thing carefully, there's a really neat prediction. It shows the thermal history of the universe. And so if you just sort of look at the lowest curve that's labeled temperature, what you see is that as you go back in time, so look at the upper axis, which says time in seconds. So as you go back towards the Big Bang, the temperature goes higher, higher, and higher. And so, there's vertical lines to the sort of vertical line all the way off to the right tells you the temperature of the CMB, which is predicted to be, a few Kelvin. But then as you go farther back in time, you get to higher and higher energies. And I just want to show you this to think about that for a moment, which is that when people build particle physics experiments, they often talk about how they're going to probe higher energies to start learning about the physics closer to the Big Bang. And that's a really exciting thing that we can do. We can now push it pretty far back. But in terms of getting to the highest possible energies, by studying the beginning of the universe, you can push it vastly farther by orders of magnitude or tens of orders of magnitude farther than what people can learn about on accelerators. And so there's this really neat complementarity between doing cosmology and understanding particle physics in the lab or in CERN. Okay, so that brings us sort of to the next point, which is that in the pictures that I've shown you, I've shown you snapshots of the universe at 2 times. Roughly speaking, you can go to now, and you see lots of galaxies, lots of stuff. The universe is filled with interesting objects to do astronomy on and to think about, and it's expanding. And then there's this other picture, which is back 10 billion years ago, a few 100,000 years after the Big Bang, where the universe was almost completely constant and was just glowing hot. And if you look at them, they look very different. Now we've got lots of structures. Back then you had almost nothing. And so the question is, does this make sense? Could we have completely uniform sky? And the answer is you really couldn't. If you have something that's completely uniform and you have forces pulling in, if you're just imagine yourself being in the middle of this, you have equal forces from either side, so you don't know where to go. And we just made a crude demonstration just for fun, because we were thinking about what fun, dangerous things we could do. And I wanted the magnets to be a lot bigger so they could be more dangerous. But if you think about it, if you have a bunch of magnets perfectly arrayed on a grid, they're just going to sit there forever, and they're not going to go anywhere. So you'll never be able to grow structures or have them collapse into things. Now, if you just move one of them by a little bit, and wow, that's really stable. That's not the right demonstration. And I'd imagined using even bigger magnets so that this would have been way more dangerous. But you get the point, right? If everything's completely uniform, you don't have any hope of collapsing to form structures. And so you just know that picture of the universe as being completely constant back near the Big Bang can't be true. There had to be some type of seeds of structure formation, little fluctuations that would later grow into form the structures that we see now. And just to fast forward, this kind of was a 30-year quest where the theorists would predict that, the signal's just below what you've just tried to do. If you just go a little farther, you'll get there. And of course, they would do the measurement and find out that it wasn't there. And then the theorists would be like, oh, no, it's just a little farther forward. And of course, it might have been really disheartening to be in this quest, but it would probably be really fun. But eventually it actually converged. And where these were first discovered was with the COBE satellite, which was a satellite that was launched in the, it was basically designed in the late 80s. I think it was launched in the very late 80s. It would have been earlier, except for the Challenger explosion. And it mapped the cosmic microwave background for the first time and actually imaged these seeds of structure formation. And for this, this led to the 2006 Nobel Prize. So this is really exciting stuff. And just to fast forward by another couple of decades really fast, this is the current state-of-the-art of all-sky space measurements, which is from the WMAP satellite, where they've now imaged the same sky to much higher resolution. And you can have a lot of fun by going back and forth on this thing. But what you can see is that the precision has gone up, even though they had the right structures early on at large scales. We can now see very, very small structures. And this leads to a lot of neat advances. One thing that I haven't talked about much is that in general relativity, you can have different types of universes that are flat, opened, or closed. And that means that the curvature is different. This data really confirms that we live in a flat universe, which is a huge advance and resolves nearly 100-year discussion of what universe we live in. And there's all sorts of other stuff you can do with it. You know that based on how big the structures are in the CMB, that dark matter had to exist. And there's just so much science you can do, and you can start asking questions about the conditions at near the beginning of the universe with it. And I'm really sort of just giving you a kind of working to bring you up to date on where CMB science stands, so I can tell you about what we're working on now towards the end of the talk. But before I do that, I want to, if you're going to build an experiment, it's really nice to have some theory for what you're going to get or some way to think about what you're measuring and why it matters. And so there's questions you could ask about this picture of the universe that I've shown you. First off, why are there these seeds of structure formation? Why does the CMB have hot and cold spots? What caused those to form? Why is the CMB almost completely uniform? Why is the universe that we see so nearly uniform that if you go that way or this way, it looks about the same? And also, why is the universe flat? So what would be really nice if you had a theory that could describe it, and we do have a theory to answer these questions, and it's called inflation, and it was developed in the sort of early 80s, or started being developed in the early 80s. And this is some pretty crazy physics, because it basically invokes particle physics at scales of possibly 10 to the 16 GeV, which, to break that down, is something like 10 orders of magnitude higher energy than what we've observed on the planet Earth at particle accelerators. So it really involves some kooky physics, but it's really a beautiful theory, and it's actually quite simple to understand, at least at a cartoon level. And so here's my cartoon guide. So if you think about the general relativity and particle physics, you could come up with if you just drew a universe out of a hat, you would draw something that could be arbitrarily weird. And I don't know how to draw an arbitrarily weird thing, except to resort to something like 80s pop art. So here's my arbitrarily weird universe. And what do the colors represent? Well, they represent just different things. So the swirls are supposed to represent curvature. You could have lots of curvature. All the colors maybe represent totally different laws of physics. And so the universe can be a very, very weird place. And what we need to do is somehow come up with a theory that gets rid of this. So this is pre-Big Bang, or right at the beginning of the Big Bang type idea. Well, how can you get rid of all this stuff? Well, in step 2 of inflation, which is really most of it, you just magnify it by a huge, huge amount. So you blow up this entire thing by a factor of something like 10 to the 30. In about 10 to the minus 32 of a second. So just instantly at the beginning of the universe, you just massively expand it. And so what does that look like? Well, you're just going to sort of zoom in. And so it doesn't take very long for everything to look completely uniform. So you have uniform temperature for the CMB, uniform properties of everything in the universe. And that happens just almost right away. But that doesn't tell you how you actually get the seeds of structure formation. But if you think about it, if you're going 10 to the 30 orders of magnitude in 10 to the minus 32 of a second, that's equivalent to roughly taking something that's smaller than a proton and making it bigger than the universe in the blink of well, not even the blink of an eye. I mean, there's billions and billions and billions of blinks of eyes in 10 to the minus 32, or 10 to the minus 32 seconds is just a tiny fraction of that. So what happens when you deal with taking small patches of the universe and stretching them to larger than the observed scale of the universe? Well, let's just think about what happens on small scales. So on very small scales, quantum mechanics takes over. And so what does quantum mechanics do? Well, one way to think about it is that there's an uncertainty principle, that if you, and one of the uncertainty principles is between energy and time. And so if you wait for a very, very short amount of time, you can't really define how much energy there is in some little region. And so if we imagine some subatomic region, which is sort of, maybe this whole yellow patch, inside of there'll be little quantum fluctuations. And just to be crude, we can think about those as like you get a little more density on the left side than the right side. And so for the next few slides, red is supposed to represent high density, whereas blue is supposed to represent low. And so quantum mechanically, this is happening all around. It's not physics that only happens in the early universe. It happens all the time. But what happens now is that if you get a little bit of a fluctuation, somewhere in the room or everywhere, wherever, it goes away really fast because you wait longer and then the energy becomes defined. So it settles down and it averages out to something, reasonable. But here, where you have this violent expansion, you have a little quantum fluctuation, and before everything can settle down, it's blown up. And it's stretched out to a scale where now quantum mechanics doesn't dictate, and it's classical, and it's a real density fluctuation. And then again, right at the same time, you have these quantum fluctuations happening all the time, so there's always more. And so as you keep expanding the universe, you keep stretching these quantum fluctuations out to larger and larger scales, and it just keeps going and going and going. But of course, at some point it has to stop, otherwise we'd live in a universe that's inflating, and that would be pretty bad because we'd be continuously ripped apart, so we couldn't come to Saturday morning physics. I think there'd probably be worse catastrophes from that than just that. But of course, it's going to stop. And at the end of that, what you have is you have a universe filled with these density perturbations that came from quantum fluctuations. And this is, again, a physicist's conception of an artist's conception of these fluctuations. But the point is that you're left with the seeds that are going to grow into the CMB and grow into the structures that we observe today. And so what I've kind of gotten you to at this point is an understanding of the history of the universe as we now know it. And this is a very beautiful picture that came from WMAP. They produced it. You can actually download it from their website called Lambda. And what it does is it illustrates what WMAP or anyone in the universe now sees if you look back, look out in any direction. And so at the very beginning, you have these little quantum fluctuations that are stretched by inflation out to these very large scales. And then in the first 400,000 years, those fluctuations grow to form the tiny temperature differences that we see in the CMB. Then over longer time scales, those fluctuations start sucking in enough stuff where they start forming stars, galaxies, clusters of galaxies. And that brings us roughly to what we have today. And so it's a really beautiful picture, and we now know this stuff pretty well. The model fits really well, and we've tested a lot of these things to percent level, which is really amazing. Now, I haven't had time to talk about it in this talk, but if you talk to Greg Tarley or other people like that, who's in the audience right over there and focuses on studying dark energy, you'll know that recently in the universe, in the last few billion years, so the last half of it, we've entered a phase where we're starting to be dominated by dark energy, which means that this model works perfectly, but you have to make something like 95% of the stuff in the universe dark matter and dark energy to fit the data. So while this model is completely beautiful and agrees with a huge range of observations, you have to just stop and ask, does this model make sense? And maybe I don't mean does it make sense, because it does make sense. Do we understand this? I mean, do we really understand it? And if we really understood it, we'd be able to know, the mechanism of inflation. We'd know what particle physics is happening at this vastly high energy scale. And we'd know exactly how the mechanism worked rather than just having a cartoon guide. Then you can also ask, what is dark matter and dark energy? And these are really great questions. And you can address them theoretically, but I'm an experimentalist. And so what I want to spend time talking about for the last little bit of this talk is the experiments that I'm working on right now. And so specifically, I'm going to show you a lot of slides of how we put together the South Pole Telescope and show you a little bit of that data. And then I'm going to just spend the last slide before I conclude showing you some of the technology we're developing for a new camera on the Atacama Cosmology Telescope called ACTPOL, which we hope to deploy in about a year. And so this is a rapidly moving forward field, and I just want to show you what the technology is and what some of the data looks like that's coming out of it. So a good starting point, well, what I worked on as a postdoc and still work on here is the South Pole Telescope. And so this is a picture of that telescope. And you may not be able to tell a scale from this, but this thing's about 7 stories tall, weighs about 600,000 pounds, and it's, as the name would imply, about 1 kilometer from the South Pole. Now, in the background, you'll see a very interesting sort of atmospheric feature, which looks like a set of rainbows. And I was so proud of taking this photograph that I started a lot of my professional talks with this slide for a very long time. And most of the time, people would look at that and say, wow, what is that? That is just totally beautiful. It looks completely surreal. And what it is it's called a sundog, which, if you think about it, you have a bunch of blowing ice in the Antarctic plateau. And so you have ice crystals that are round. You have ice crystals that are sort of hexagonal, and you have other ones that are needle-like, and they all settle in the atmosphere differently, and that leads to these sort of different shapes that come up there. And I was really proud of this, and as a former Californian, I just thought this was one of the most mind-blowing things I'd ever seen. And then I went up to Minnesota and gave a talk, and before I could open my mouth and share my joy for this new finding, they all said, oh, wow, it's a sundog. We get those all of the time. So I'm glad that we're not quite as cold as Minnesota. around here. So anyway, that's the South Pole Telescope. If you look at it from the air, this is what you see. And so I've put in a map to remind you of where we are. We're talking just at the South Pole. The South Pole is actually just a little bit off the screen to the right. When I was putting this talk together, I thought about diving right into how we put the telescope together and all that. But I realized I have this really rare opportunity with this audience to just tell you how we get to the South Pole and show you some really fun pictures that I took along the way, which is complete fluff, and I wouldn't get away with professionally. But man, it's so much fun. So, down here on the bottom right, I've shown you a map, and it's got this sort of 1950s style movie little flight path on there to tell you how we get in there. And that flight starts in New Zealand, in Christchurch, which is where that terrible earthquake was this year. And what you do is you go down to this air base, and you get on one of these. It's a C-17. Thank you, I forgot. It's a C-17. And you hop on there, and you fly over the over the ocean, and you land in McMurdo, which is on the coast of Antarctica, where that dot is. And you get off the plane, and I was very surprised to see that my nose hair froze right away, and it wasn't even really that cold. It was probably like -20 or something, -15. And if everything goes right, you just get on a plane and fly right to the South Pole a couple days later. But occasionally, you get a really bad delay, which can be a little disappointing, except that you're in Antarctica, so it's actually kind of fun. And so the worst delay I ever had was about 14 days where I was stuck just hanging out on the coast of McMurdo, and you get to do some fun things. So one is you get to drive around in this really cool vehicle, which is called Ivan the Terrabus. I don't have a side view of it, unfortunately, but it's a nice red thing. And you get to drive out and see the southernmost volcano and drive out on the Antarctic Sea. We're actually on the ocean right there. And as you're driving, you get to see some of the local natives. And we drove up on this trip, and we saw a bunch of penguins about a mile away. So we all hopped out of the car, and we started taking pictures of them. And I really thought it was the most amazing, beautiful thing I'd ever seen, with the penguins so small away that they only looked about an inch tall in my viewfinder, and you could barely see them. They were dots. But penguins don't have any predators on land, so they saw a bunch of weird people they'd never seen before, and they were more excited than us. So they walked over, and they actually got, I was taking pictures, so I didn't realize how close they were until they're about 3 feet away. And these things are just, they're about this tall, and they make, really cute penguin noises. It's great. So that was fun. And then, we continued on our trip where we're actually going to an ice cave, and this is what the inside of an ice cave looks like. And I'm partially just showing this off because I like the picture, let's be honest. This is another view from there. And so it's just really miraculous. Now, of course, where we are at the South Pole is far away from there. So you have to get onto a ski plane. And this is labeled as an LC-130. It's actually an HC-130. And the H is for the fact that you put skis underneath it. So it's actually a big military ski plane. And I told you before that the South Pole Telescope weighs something like 600,000 pounds. But the maximum capacity of these things is about 26,000 pounds. So this is like a child's toy in the 80s, where our telescope has some assembly required. In fact, if you add it up, just to be able to put our telescope together and fit it in the plane and put it back together, we had something like 50,000 pounds worth of bolts and hardware that we had to carry into the South Pole. But you get on these planes, and you fly in with the cargo, and this is what it looks like on the inside. And one thing I haven't told you about the South Pole is that it's really high altitude. It's about 11,000 feet. And so before I got on this plane, there was a military Air Force flight surgeon who said, you're going to take this medication so that you won't get altitude sickness. And it really is the right thing to take for altitude sickness. And of course, me being the person I am, I raised my hand and said, what are the side effects? And him being an Air Force flight surgeon said, well, look, I could tell you for hours about all the possible side effects, but we both know they won't happen. So guess what happened? Yeah, it's a glaucoma medication, and so it actually made it so that I couldn't focus my eyes farther than putting my hand on my retina. And so this is me flying in to the South Pole for the first time. And if you just look at my eyes, they're kind of cross-eyed, and they're not pointing in any particular direction. It's because I was totally blind at the time. But luckily for me, I could still see the mountains when I looked out the window through my camera, and they were just gorgeous. And so these are, I don't even know how tall the mountains are, but they're very, very tall peaks, but they're covered in snow. I mean, it's just totally, totally packed. And so you land at the South Pole, and you're on about 500 feet of rock and a couple miles of ice. So you're at about 11,000 feet, just under 11,000 feet. And if you look out away from the station, it looks like that, just totally desolate land, windswept and empty. Of course, you can't help but going for a photo op, because I mean, seriously, you feel very lucky when you get to take this picture. But then you turn around and you walk towards the station and you think, oh my God, I can't tell anyone that I'm roughing it. This is just so lavish. So this closest sort of big wing of the building with no windows on the bottom, at the lower right, lower left, is actually a full court basketball gym. And so anyway, I can't really say that I'm rough and tumble or too adventurous compared to the early explorers at all. But now getting back to our story, I really want to tell you about building this telescope. And so I told you there were a lot of parts. We're actually sitting here right at the edge of the runway starting to put together the mirror. And I think on the days when we started, it was the very beginning of the season. So I think it was late November. So it was very cold. It was, I think, -50 with a wind chill to -90 the days we were putting this thing together. So I guess I can kind of claim that as my rough and tumble rough and ready history, but it was quite cold. And so we started putting this thing together, and you see these big carbon fiber panels that go on. Those actually hold the mirror. And if you think about it, if you're going to be out in temperatures that range from 0 to -100, which is where the telescope operates, you've got to make sure that thermal contraction doesn't change the shape of your mirror. Otherwise, you have a fun house rather than a scientific instrument. And so we were really careful to use materials that don't have a thermal contraction. So we did this right by the edge of the runway just because it was the easiest way to assemble it and move it. And if you notice, we're building it on this giant sled, which is actually a Canadian-made sled that they make for oil exploration. And so when we were ready and had the whole thing assembled, we took our flying saucer-looking thing on our Canadian sled and transported it across where we were going to build the telescope. And I just get so much amusement from this because if you think about it, when do you really get to play with giant Tonka trucks that are real? I mean, I have so much fun in my job. Once we'd done that, though, the real work started, and we had to put together the mirror, which was made out of 218 panels of aluminum that had to be, tiled to better than about 1/100 of a millimeter, 1/10 of a millimeter. So it was really quite a job. And so that's me in the middle. You can kind of barely make me out. I'm sort of, over this theodolite, which is a surveying tool. And you may notice that my colleagues are all wearing big red parkas, but I'm not. That's not because I'm dumb or because I'm brave. It's because I had to, because if I bumped that thing, I could throw it off and we'd have to start over with the panels, which, on a month job, when you have a month to do it, isn't really a good call. So I ended up eating a lot of bacon to stay warm. And in fact, like one morning I came in and I had consumed, we were on night shift, and I ate a plate of bacon followed by a plate of bacon. And I'm actually, this is literally the size I'm talking about. And then they were out of bacon, so I only got about a half plate. But I managed to consume about 10,000 calories probably in one sitting. And I came off the pole a pound lighter than I went in, which is sort of amazing. Bacon's tasty. Okay, anyway, sorry, I'm totally digressing. I want to get back to the whole point, which is cosmology. And so this is what the mirror looks like when we're finished. And I just can't tell you how excited I was when we saw this whole thing together for the first time and ready to be lifted onto the telescope. And then when we lifted onto the telescope, that's where it got incredibly exciting because, well, one, we had to use 2 cranes because there wasn't a big enough crane down there. So it was a really coordinated, hard piece of construction. But it was just beautiful watching it all go together. And then at the end of it, we had something like this where, we got to go out there and stand there and take kind of the glamour shot. Now, of course, there was a lot of very hard work because we still had to align this thing. And in fact, if you notice, I put my initials on the mirror, which I don't know if that many people in my collaboration know I did. But I did it for a reason, which is that I wanted to make sure I knew how to measure the height of the mirror and had everything in the right alignment because I was using this technique called holography to figure out the height of each panel so I'd know exactly how to align them. And so I put a bunch of aluminum tape up there in a particular pattern just so that I'd be able to tell that I was doing things right. So I'm glazing over a lot of work that went on to really be able to get this telescope ready. I haven't told you really much about how the camera works, but I will tell you that the camera that we have on this telescope is one of the most sophisticated cameras for millimeter wave technology that's ever been built. In particular, it has about 1,000 pixels, so it's a kilopixel. That may not sound like a lot, but if you think back, in 2000, when I came to grad school, I worked on an experiment that had 1. 1 pixel. And here we are 10 years later with 1,000. That's actually pretty good. That's basically a Moore's law. And you can chart it in between, but the progress has been incredibly rapid, and with that comes incredibly beautiful maps, which I'll show you in a bit. So at the end of, you notice that every picture I took of the telescope was during the day. There's a very good reason for that, which is the sun never sets in Antarctica during the summer. I've only been there in the summer, so therefore all my pictures are of it during the day. And at the end of it, when we were ready, we flew out. And this, of course, isn't our flight because I took the picture, but this is what it looks like. This is what it looks like when you see a plane take off and the weather conditions are right so that you get a nice contrail right on the ground. And it's a beautiful place. So we leave when it's still beautiful. It gets even more beautiful in the winter, which I've never been there for. But my friend Keith Vanderland, who stayed down to make sure the telescope worked, and every year we leave a team of a couple people there to make this whole thing work, keep it up, and get all our data, because we only take data during the night, which is about 6 months. Anyway, he took a lot of beautiful photographs. So you see the aurora, the galaxy in our telescope as it looks while it's observing. And I think Keith just did a beautiful job on these. What's even better is that we get data out of it. And just to give you an idea of what our data looks like, I'm going to first show you data that didn't come from our telescope. So this is what came from the WMAP satellite. If you look at a region of sky that we're going to map with our telescope. So it looks beautiful. You see all these fluctuations. Those are seeds of structure formation. But when you zoom in it with our telescope, and these should be the same parts of the sky, you just see all this rich detail pop out that you couldn't have seen before. And it's really beautiful. And there's a lot of stuff I want to direct your attention to. Now, one of the things that comes out first when you look at this is that there are a bunch of bright point sources. So those are galaxies, and those are astrophysics. And there's interesting cosmology you can do with those, but it's much more, what I really want to focus on for this talk is cosmology and what you can learn about the universe from this stuff. And so there's sort of 2 things I want to direct your attention at. First off is that there's a lot of small scale features in here. And using this high resolution data and looking at the shape of the small scale features, or the number and amount of small scale features, we were able to probe inflation and put constraints on models of how inflation was driven. And that's a really exciting thing that we're now able to start doing. Another thing that's one of the main reasons we built this telescope is that if you look, here, let's just go back. Notice where that circle was. Notice that there's a nice big dark spot right there, right? That dark spot is a cluster of galaxies, and they leave this really unique signature in our data, which is little dark holes. And if you look for those things, and we have very good ways that are very sophisticated to do it, you can find clusters of galaxies, and those are the largest condensed structures that are in our universe. And using those, I'd love to tell you more about it in another talk. You can understand dark energy, and that's one of the exciting things we're doing. So the point I want to make is that by making better measurements, you can understand the full range of things over the whole history of the universe, from inflation on the earliest times down to dark energy and dark matter at more recent times. But of course, we'd like to do even better. And so to march forward, we want to march technology forward. And so we've been working on new cameras that'll go both to the South Pole Telescope, and also I've also become engaged with the Atacama Cosmology Telescope to work on their camera. And this is just sort of I just want to give you a feel for what types of stuff you build to build a camera. And so there's a whole lot going on in this picture. But one of the key technologies is these detector arrays, which this shows a prototype array with about 160 pixels in it, or maybe I mean 90. I forget exactly how many were in there. But we've worked very hard to develop these new monolithic arrays of detectors so that we can improve our cameras. And one of the big things that we're going to do is that these cameras are going to be polarization sensitive. And if you think about it, you probably have all put on polarized glasses at some point, and you've walked around and you notice that if you tilt your head to the side, you can change the color of the sky because light is inherently polarized, or you can get rid of reflections off your dashboard. Well, the CMB is also polarized, and there's this really miraculous thing that I'm going to very much I would love to spend a lot more time talking about, but I'll just whet your appetite, which is that inflation produces these density fluctuations, but it's also incredibly violent. It's violent to the point where gravity is actually getting dragged around too, and so you actually get gravitational waves that fill the universe from inflation. Now, what's really neat is that those gravitational waves propagate around while the CMB is being emitted, and they leave this polarization signature on the CMB that you can image if you have polarization sensitivity. And with these maps that I've shown you so far, we only have temperature sensitivity. So what you really need to be able to go after this measurement is sensitivity to polarization, and that's exactly what we're going to do. And if you go out and make polarized maps of the CMB, there's a very unique signature that you can see that will tell you the energy scale of inflation. So you can start understanding more of the details in a way that's really quite wonderful about how inflation actually happened, and that's one of the goals that will happen from these projects. Another thing you can do is understand the recent universe by using polarization to reconstruct where all the matter is along the line of sight. And so this technology is going to really push things farther forward, even beyond what we have right now. So I'll just wrap up by saying that the hot Big Bang model is absolutely beautiful, and we've worked out a lot of the details. We know it's expanding. We know there's background radiation, and we actually have really good ideas about how to understand how the fluctuations got there in the first place and what their structure is. But there's many mysteries left to solve. We still need to figure out what fills the universe, what dark matter and dark energy are, and also what happened at the first few moments, which is kind of the idea of inflation. And the new instruments that we're working on will hopefully shed a lot of light on this and really help move our understanding of cosmology forward. So thank you very much.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.